The next concept we're going to be learning about is something called calorimetry. Now, calorimetry is an actual lab technique that is used to determine how much heat is being transferred from one substance to another. And you notice here it says that it can be in chemical or physical processes. We are going to be focusing on the physical ones. In our studies, we're just going to be transferring heat from one thing to another simply by placing them in contact with each other. But the whole chemical idea would be an actual reaction taking place, like actual new products forming. We're not going to be worrying about that type. What we're going to be doing is things like heating up a piece of metal and placing it into a cup of, say, cool water and seeing how the heat transfers. Now, the biggest issue you can run into with this is that if we want to see how much heat is transferred from one substance to another substance, heat can't leave the reaction. You don't want the heat to escape into the surroundings. Envision, say, a pot of water boiling at home. If you put your hand above that pot of water boiling, you can feel the heat escaping to the surroundings. Well, we don't want that heat to escape. We want it to stay trapped within the reaction vessel, so that we don't have to worry about heat being lost, and we can truly test to see how those two things are exchanging their heat. So how are we going to do that? How are we going to make it so that we don't lose heat to the surroundings? The way we do that is by using something called a calorimeter. So this is called calorimetry, and calorimetry uses a calorimeter. Now, in front of you, you have your notes. Oops, sorry about that. You have your notes. You should be taking notes, so you've already filled in this part here, and now we are at the point where you should be working on this part right here. So a calorimeter is an instrument that's used to minimize heat loss to the surroundings. So again, it's trying to keep the heat in. Try to think of something that you might know of out there that does that allows the heat to stay in instead of being allowed to escape out. If nothing's coming to mind, think about maybe a trip to, say, Starbucks or to Circle K to get some coffee. If you have the regular paper type cups and you grab a hot cup, you can definitely feel that heat. But if you have a styrofoam cup, you don't feel the heat on the outside of the cup nearly as much, if at all. And honestly, it might not sound that fancy, but most of our calorimeters are just simply that. They are just going to be coffee cups, as you can see here. So what we usually do is we're going to be taking these coffee cups, 2 coffee cups, and we're going to put them nestled inside of each other. So you can see there's 1 and then there's 2. And then we have some sort of top on it. This one says a cork stopper. We usually just use another styrofoam cup to insulate up top. You do need to use something else as a good insulator. A regular coffee cup lid is not very good. You see there's a hole to have a stirring rod because we want to constantly be stirring during this process, and then we of course need a thermometer or else we won't be able to watch what's happening. And essentially what you do is you put the water inside the cup. Okay, room temperature water usually works best. You measure its temperature to start with. Okay, then somewhere else you are heating up your substance. Most of the time that will be a metal. So you're overheating up your metal somewhere else. You measure its initial temperature, the metal, and you measure the water's initial temperature. Then you quickly take this lid off. You dump the metal inside that container, and then you quickly put the lid back on. You start stirring constantly, and you see what happens to the temperature. We know that if we put something hot into something cool, that the hot one will cool down, and that the cool one will heat up, and they'll eventually get to something called thermal equilibrium. Okay, thermal equilibrium means that they've achieved the same final temperature. So their final temperatures will be exactly the same. Okay, their final temperatures will be exactly the same once the reaction's finalized. And remember, if you have water in this cup, water has a very high specific heat capacity. So what you'll notice is that water's temperature doesn't change very much, but the metal temperature changes drastically. And you'll see that in some of the examples we're going to get to. So I just kind of explained this process, but let's go ahead and get it into your notes. So how a calorimetry experiment works. First, water is placed into the calorimeter and its initial temperature is taken. That's a very important step. After that, the second substance, which in most of the cases for us is going to be a metal, is heated and its initial temperature is recorded. Most of the time we heat that metal in for example, boiling water. So usually its temperature is going to start right around 100, but it doesn't have to be. But you'll notice a lot of problems will show like that. Then we are going to, sorry, it's very exciting, isn't it? Then we're going to take both the masses of the water in the cup and the mass of whatever substance it is that we're heating up. And again, when I say substance, most of our problems are just going to be a metal. Then you're going to take that substance, so it's really hot, it's been heated up somewhere else, and you're going to very quickly is the key word here, place that substance into the water. You're going to get the lid on, and I don't see that written here, so somewhere around here, write down, place the lid back on, and you're going to record the temperature change in the water until the temperature is constant for a number of readings, okay? And the calorimetry, we actually monitor it the whole time, and then you'll notice eventually it will reach thermal equilibrium. It will be constant for a number of readings. Then the final temperature is recorded. Notice it doesn't say final temperatures, it just says final temperature because they'll both be at the same temperature in the end. Okay, that's the point of placing them within each other. Now we're going to go ahead and try a problem. We'll actually do two on this video lesson. The first problem, notice it seems so long. It seems like there's so much information. But again, that's the point of writing out all our givens, is to sort of get rid of the words. Don't tell your English teachers, but we'll get rid of the words and just deal with the numbers that we have at hand. If it's a calorimetry problem, you're going to be given lots of information, but it's going to be about two different things. So in this problem, we read that they give us the mass of a piece of copper. They give us its temperature, and that it's going to be placed in a calorimeter. Then it tells you about the water in the calorimeter, how it starts off at 23 degrees Celsius. Then they tell us the solution came to equilibrium at 24.8 degrees Celsius. So 24.8 degrees Celsius is the final temperature. But remember, it's the final temperature for both of them because they will both ultimately end up the same. And they want us to calculate what the mass of the water in the calorimeter was. So what I want you to do is pause the video and get all of your givens written out. So this is what you should have for your givens. Notice here that I have taken and put copper and then water and listed my givens separately. I think that's the best way to do it so that you don't get confused. All right, what we're going to do here is I'm going to kind of walk through this problem. You can use the pause button if I'm getting ahead of you. Remember to kind of stop. Make sure you're going at your own pace. And of course, you're going to be recording this problem into your the notes paper that you have. So what we're going to start by doing is dealing with the one that we know everything about. Now, what do I mean by the one we know everything about? Notice that Q equals MC delta T, that equation has 4 variables. So look on your givens and see which one you have everything about, okay? Everything that you need to be able to solve that problem, okay? Actually, when I say 4 variables, I kind of referred to delta T as 1 variable, but remember delta T involves 2, so we actually have 4 of the 5 that are needed, which is good, because obviously if you don't have a variable to solve for, that would be very odd. So whichever one you have more information about, you're going to start with. So if I see here I have 4 pieces of information about copper and only 3 about water. So I'm going to go ahead and start by doing a calculation with copper. Now, we're going to be using Q equals MC delta T only for this because we're not changing phases. This is simply heating and cooling. So you write out your equation, then you're going to plug in your variables. So you're going to plug in that mass that you have. You're going to plug in your specific heat capacity of the copper, which was given to you in the problem, and then your change in temperature. Don't forget, it's T final minus T initial. Okay, change in temperature, T final minus T initial. Then I'm going to go ahead and solve. I'm going to plug all those numbers in. When I do so, I get negative 10.776, and the unit for Q is, of course, in joules. And then I'm going to not round at that point. And I don't want to round at that point because we have not gotten to our final answer. This number that we've got right here is the heat lost by the copper. You see the negative indicating lost. That's how much heat was lost by the copper. Now take a second and think about this. If I have an insulated container and copper lost 10.776 joules of energy, then how much energy did the water gain? If you said that same number but positive, you are absolutely right. So heat lost by copper was negative 10.776. So that means the heat gained by the water must be positive 10.776. Of course, joules. Now, why is that helpful? Well, we are trying to solve for the mass of the water. We know the specific heat of it. We know the TF and TI. If we know Q, then we can plug in and solve for mass. So we're going to write out the equation for the specific heat capacity of water. So again, we're going to just use Q equals MC delta T. Okay, so I plug in that positive 10.776. You have to change that, okay? You have to change it from whatever you find the Q of the other one to be. It's always the opposite sign. Plug in my variable, which is the mass. I plug in my 4.184 and my TF minus TI. Now it's just a matter of solving. Divide over the 4.184 and divide over the 24.8 minus 23. Remember, order of operations is important. And you should end up with a mass of 1.4 grams of H2O. So again, I used all these variables. There were so many, but it really is a step-by-step process. See which one you have the most information for, solve for Q. Then you're going to take that information and plug in the opposite signed Q into the other problem. Okay, let's go ahead and try another one. Here we have another problem. This time we're putting titanium, that's at 99.5 degrees Celsius, into a calorimeter. This time they tell us how much water is in the calorimeter, but they want us to find the specific heat of the titanium. So we are going to be solving for C of the titanium. So go ahead and pause the video and get all of your givens written out, remembering to make two categories, one for titanium and one for the water. Now your givens should look like this. Make sure you have them all. Now take a peek here and see that you have 4 givens for the water this time and 3 for the metal. So we're going to start by using the information that we have for the water. So I'm going to write the equation for the specific heat capacity, but we're going to be plugging in the information only about the water. So the Q we don't know. We know the mass at 75.0. Specific heat capacity of liquid water is always 4.184. And then delta T is going to be final temperature, which is 24.3, minus the initial temperature, which is 21.7. Then you're going to plug all of that in your calculator, and when you do, you end up with 815.88 joules of energy. Now, just like last problem, we discussed and said that that is the amount of heat that, this time for water, and it's positive, so it's the amount of heat gained by the water. Okay, the amount of heat the water is gaining. So that means the metal lost that much. Now, I'm about on this video to write down what Q is. I want you to see if you can write it. Okay, let's see if you got it. So you should have said that the Q for the metal would be negative 815.88 joules. So that now gives us another piece of information about the titanium. So now we can take and plug in Q equals MC delta T. Looks like I didn't write it. Remember, it's always good to keep this stuff labeled. So if you want to, this is really hard to write on here, but oops, titanium. Oh my goodness, that looks horrible. Okay, hopefully yours looks better. So we'll label it as titanium. It just makes it so much easier. Okay, and then we're going to go ahead and let this continue. Okay, so we're going to plug in our negative 815.88 as our Q for our titanium, plugging in our mass. Now we don't know C. Remember, we're solving for specific heat capacity. And then we'll plug in our final temperature, same as water's, but our initial temperature was much hotter, 99.5. and I'm going to combine everything over on the right side so it's a little easier to solve. When you multiply 20.8 times that change in temperature, that's what you get. And then divide over, and your specific heat capacity comes out to be 0.522, and the unit is joules per gram degrees Celsius. Remember, that's always our unit on our specific heat capacity. Now, before we go away from this problem, I want to show you something. I want you to kind of acknowledge and see this on this, that it's kind of interesting how the water, where's the water? Here it is. The water's temperature didn't change very much, like, 3-ish, not very much. But the metal's temperature changed a lot. And that comes from the fact that the specific heat capacity of the metal is so much smaller. It gains energy and its temperature changes drastically. That 4.184 number is telling you that water is a very good absorber of energy. It absorbs energy without a large change in temperature. So I just wanted to point that out while we had this problem in front of us. Now, if you need to, you can go back and rewatch any part of this that's necessary. But if you're looking at this and feeling pretty comfortable with it, then you can go ahead and get. Now, for the homework, your paper looks like this. First part of this is just, fill in the blank, making sure you understand your definitions. The second part is identifying your variables, making sure you're clear on all of that. A conceptual question. Now, what I really want to point out here is on number 12. A lot of students on number 12 will try to use what we just learned. But if you notice, it's only talking about iron. It just says how much heat, which is Q, is required to raise the temperature of 20 grams of iron from 26 to 72.3 degrees Celsius. And they give you the specific heat of the iron. That's just a one-step Q equals MC delta T problem. It's not till you get down here to number 13 and 14 that you're going to be doing more than that. Okay, these ones involve a metal and water, a metal and water. So that's how you're going to tell the difference. So the beginning part of these problems is much more straightforward. Number 12 is an old type Q equals MC delta T, no fancy phase changes, nothing crazy. And then 13 and 14 are going to be like what we just did. Okay, so good luck. Rewatch what you need to watch, and we will spend more time on this, but make sure you get this homework done for tomorrow.